Hello everyone, my name is Mengzhu Gao. I'm a graduate student at UC Davis in the Department of Mechanical and Aerospace Engineering. Today, I would like to present our work, Temperature Sensor Deployment for Scalable Battery Packs, with co-authors Qinzhi Lai and Professor Xinfan Lin. First, let's look at the background of this research. The capability of temperature monitoring of a battery system is important because we need to ensure the safety during the operation. In addition, the key performances such as power capability and cell degradation are largely impacted by cell temperature. One critical issue for temperature monitoring is battery pack sensor deployment, because there are a limited number of sensors in the battery pack. For example, in the electric vehicle, typically the ratio of sensor to cell in the battery pack is less than 1 to 10. And the sensor locations are important because it determines the system observability. To tackle this issue, model-based approach have been used for the temperature estimation, such as a closed-loop observer and common filter. Regarding the work on sensor deployments, the rank of observability matrix, eigen decomposition, and observability Gramian criteria are used to determine the optimal sensor locations on the battery string or battery pack. However, there are still challenges and gaps exist. Currently, battery string thermal model cannot completely represent the thermal interconnection in the pack level. Furthermore, previous work did not look into the sensor deployment patterns in the battery pack, and the influences of critical parameters on observability haven't been explored. Our contributions are as follows. First, we developed the 2D battery pack thermal model for the estimation and observability analysis purpose. Second, optimal sensor deployment patterns are founded under different observability criteria. Finally, we have investigated the influences of critical parameters on the system observability. Now let's look at the battery thermal model. The single-cell or string thermal model had been proposed in the previous work of our lab. In the single-cell thermal model, the core temperature dynamics includes the heat generation and the heat conduction between the surface and the core. And the surface temperature dynamics include the convection between the coolant and surface and the conduction between the surface and the core. The battery pack thermal model developed here is expanded from the single-cell thermal model, and adding the extra heat conduction between the adjunct cells and heat convection between the coolant and surface. Note that in the parameter n, in the equation of heat conduction between the adjunct cells, represent the number of the neighbor cells. If the battery is in the corner of the battery pack, n equals to 2, and if it's in the edge of the battery pack, n equals to 3, and if in the middle of the battery pack, n equals to 4. Now let's look at the section of the problem formulation. In the control theory, observability Gramian provides the quantification of the system observability, which is defined as the following equation. Gramian can be calculated by solving the following Lyapunov equation. The two scalar matrices of Gramian are used as a criteria for observability analysis. One is the trace of Gramian, which represents the overall system observability, which equals to the sum of the diagonal elements of Gramian, or the sum of all eigenvalue of the Gramian. The other is the minimum eigenvalue of Gramian, which represents the worst-case observability. The optimal sensor deployment problem can be formulated as a set function optimization problem, and the cost function is shown as follows. In the equation, A is the state matrix obtained from the battery pack thermal model, and S is the set of all possible combinations of the sensor locations. In state matrix, the number of rows denoted the number of sensors. Note that in the state X, even entries are the surface temperatures, So in the same matrix, the even entries with element 1 means that the surface temperatures can be measured by sensors. Function f can be either trace metric or minimum eigenvalue metric. Now let's move forward to the results and discussion section. The optimal sensor deployment patterns are obtained by maximizing two Gramian-Based metrics. For the trace metric, the sensors are located at the corners or edges of the battery packs. We also give the mathematical explanation of the pattern. Based on the property of trace of matrix, the trace of Gramian can be rewritten in the form trace of CX transpose, which is equals to the sum of the diagonal elements of X that are selected by C matrix. Since A is diagonal dominant matrix, based on the equation of X, X is largely determined by diagonal elements of A, that is AII. Maximum trace metric under certain C matrix is equivalent to picking the largest AII, and AII takes the form here. Therefore, when parameter n reaches to its minimum, which is 2, means sensors are at the corner of the battery pack, AI will be the largest. Let's give us the explanation why sensors are located at the corners or edges of the pack under the trace metric. Under the minimum eigenvalue metric, sensors are more evenly distributed in the battery pack. Because the minimum eigenvalue represents the observability of the least observable directions in the state space. If the sensors are concentrated in certain areas of the pack, the temperatures in other parts are poorly monitored. We also investigated the influences of cell-to-cell conduction resistance and spacing on the two metrics. For RCC and ST, it has the monotonic increasing relationship with trace metric. The explanation is similar with the pattern under trace metric. Since trace metric is determined by AII, when RCC increases, AII will increase accordingly. Then the trace metric will have a larger value. For ST, it has been proved that ST has a monotonic increasing relationship with RU. Therefore, when ST increases, AII will increase accordingly. With regard to minimum eigenvalue metric, RCC has non-monotonic relationship with minimum eigenvalue, while ST has monotonic increasing relationship with minimum eigenvalue metric. Finally, let's look at the conclusion and future work. To sum up, in our work, firstly, we obtained two sensor deployment patterns under two observability metrics. For trace metric, sensors are located at the corner or edges of the battery pack. For the smallest eigenvalue metric, sensors are more evenly distributed on the battery pack. We also give mathematical explanation on the theoretic underpinning underlying the patterns. Finally, we have investigated the influences of critical parameters on the two observability metrics. The future work includes design a closed-loop observer based on the optimal sensor deployment patterns and comparing errors with that based on the baseline deployment. In addition, other criteria and methods for sensor deployments can be explored, such as data-driven method. Thank you.